again. Good morning. Gaétan Leclerc. Well, tell us about technology mix and further interview like this.
Okay, thank you very much for that introduction. This is supposed to be an informal talk, so I hope it will be alright because I did not prepare it as well as I have other tools. Don't hesitate to interrupt me as yesterday. Today it seems that there is going to be a theme around point decay in some way. So there is a message that I would like to tell you today. I'm not going to discuss that much point decay, but it is related. The message is that in some way, exponential mixing and point decay are the same problem. And today I will somehow explain to you how you can use point decay to establish exponential mixing. And 7 will explain to you tomorrow, I think, the other side, in some sense. This will be very elementary. I hope it will be easy to follow. Let me define what I mean by exponential mixing. So exponential mixing, what is it? So we start with some measure preserving dynamical system. We fix some map F in some space, leaving invariant some probability measure. Some Borel probability measure. Let's say that X is a compact. And you need to fix the space of function on X. And then you say that your dynamics is exponentially mixing with respect to this measure and with respect to F, the following model. With respect to F and U. If when you choose two maps, H1 and H2 in your space of function, the following happens. This quantity will converge to this product of integrals. And so when this happens, you are just mixing. Exponential mixing means that this happens exponentially fast. So the current term will be some exponentially decaying term, so you want some alpha such that positive. Okay, so what does it mean intuitively? It means the following. So for example, so those things you call them observables. So an observable is some real value associated to your state. For example, if your state is so your phase space is S, you can take H1 to be something that looks like a characteristic function of some set. Okay, you can make it continuous if you want. And then this is the probability. Okay, let's take H2 the same for some other part. This here in this case is the probability of starting from B and falling in A after n steps. The fact that this probability converges to this one means that those two events are decorrelated as time goes on. So this is a decorrelation property. Another way of writing this is to recognize that this is like the expectation of some quantity. If you want to write it as using a more probabilistic. So this is a random variable. This is a random variable, and exponential mixing means this. So this is a decorrelation statement. Now, pictorially, what it means is that if you look at the free image of A, A should densely live a little bit everywhere. It should not miss any path. So if you take n very large, you should see f minus n of A that looks like this way. It needs to fill up everything. And the more n grows, the more you fill everything without leaving any single space. That way, if you choose any open set B, indeed at some point you will laminate it. Okay, so that's what we need to meet exponential. This is an important visualization because it means that you can decide with your own eyes when something is exponentially mixing or not. If you are looking at a dynamical system which is not twisting, which is not expanding like that, you are sure that it's not going to be exponentially mixing. For example, rotation, you are done. You don't need to write anything down. You can just sit with your eyes. Okay, so let me give you one example. Okay, maybe first, as I said, maybe one example. It's not right side. So one example would be rotation, empty tab acting on the torus. This is S1. This cannot meet because if you look at some open set A and you look at the pre-image, it's not going to fill up everything, it's just going to be the same. I mean, yeah, you can just okay. Now, one example which is easy is expanding maps. And we are going to put it in another example. Hopefully, we'll have the time to say everything I want to say, but we have a couple of days after if you want more. So, okay, a lot of expanding maps, but let me just take one example. Let's consider the doubling map. So the doubling map for me, okay, I'm going to write S1 or T depending on my name. Take some X, maps it to 2x modulo 1. So this is the doubling map. It lives invariant in the measure. On the circle. And it is going to be exponentially mixing with respect to the Wig measure for some space of function, say a third of regular functions. And we are going to call it because it's not very hard. Okay, so first of all, I need to introduce a tool which is very important for me, which is transfer operator that you probably know already. Okay, but this allows me to fix notation also. So this is my circle. Okay. The doubling map sends this whole part into the whole circle bijectively, if you forget about the endpoints. Say like this. So you can consider the inverse branch. I'm going to call them G0 and G1. So we have formulas. G0 of x is just x over 2, and G1 of x is x over 2 plus 1. So J0 sends the whole circle here, in this S0 part, and J1 sends the whole circle into this circle. Okay. So this gives you an IFS on the circle, and then I'm going to use all the usual notations for IFS, position, etc. with words. Okay, so an important remark is that in this case, the Lebesgue measure is a self-conformable measure for this IFS. So I just like to stay simple, but everything I'm going to say works for any self-conformable measure, I'd say. Okay, so this I'm going to denote by transfer operator like this. Okay, which means, as you know, that when you integrate with respect to the Lebesgue measure of the circle, you can make a transfer operator like that, and you can pick as much as you want. Okay, so I think that's all the tools I need to use. Let me just write the notation for this. This is what? So when you compute what is this quantity, you get H composed with J, A, X. Up, like that. All of this, I like doing this with the Lebesgue measure because you can prove this just by the integration by parts elementarily. So I think it's a great example to start when you want to explain transfer operator to students. Also, Lebesgue is the measure of maximal entropy of the building map, so it makes sense that there is an entropy dimension. Okay, one last fact that I need is that if you use a transfer operator on H1 of 2x times H2 of x, and you compute what's happening, H1 of 2x, x will be replaced by the inverse branch, it will disappear, and you will be able to put H1 at self. I can put it if you want, but I'm not sure if it's very interesting. Okay. So maybe for those of you, I'm not sure. So do you all know what is a transfer operator or not? Yes, no? Okay. Because I can adapt my skill. So acting on functions, this is the formula. And by definition, the inverse branch, when we look at 2 times GA of x, is going to equal to x. Okay, so exponential mixing. We take 2 functions, say they are alpha or beta, and we want to study this quantity. So actually, the real definition of the transfer operator is that this is the adjoint of the precomposition by the dynamics. So it makes sense that the transfer operator is going to look at here. You can also find it that way. So you can apply your transfer operator 10 times. And then you can put this outside. And essentially, you have almost already done. Because if you just look at this quantity and trying to understand very hard what it does, it's literally a Riemann sum that converges to the integral of A between 0 and 1. So the point is that when you have a word A, this is going to send the whole circle into GA of X, so into this part, SA. This is a DLD decomposition of every point in the circle. And so you are sending over every DLD points on the circle, you take an average, so obviously you converge to the table. And since you have alpha order, you have an error term which is the diameter of this over alpha. So you get 2 to the power of minus alpha. And then you're done. So very easy. Completely every. And we are done. Okay, so essentially, when you take any extending map, this line of reasoning will work. You need a little bit more tools. You need to define properly what you are looking at for the invariant measure. Typically, you use the thermodynamical formalism to introduce equilibrium states. You need to operate for minus square. Seems very abstract if you are not used to it, but it's literally this. So not that bad. Okay. So extending maps, easy case. What else can we do? We can do hyperbolic diffeomorphisms, like for example the cat map on the torus. This is also a linear example, but this is just to make the computation easy, but you don't need to take linear example. You see that the method I presented to you is very old. So another example. Hyperbolic reasons. I'm not going to be very precise on this, let me just explain pictorially what it means. So for example, on the torus T2, you can find linear maps, which are called the cat maps. So typically you say that something is hyperbolic if you have a direction in which you are expanding and a direction in which you are contracting. Like that. In this case, you can again see with your eyes that this is going to be exponential mixing under very little assumptions. Because if you fix a little set A, say here, and if you look at the backward orbit, but if it's a diffeomorphism, you don't care, you can take forward orbits, you are going to become a very, very long spaghetti. And since for these hyperbolic diffeomorphisms, this direction is irrational, you are going to fill everything like that, following some irrational direction. And the more you iterate, the more you fill everything. So again, nothing to prove essentially, you can just say it. We see it. Okay. So it's clear that it runs. You can adapt the proof of this case by reducing to the one-dimensional setting by saying that when you iterate very long, the stable direction will become invisible because since you contract a lot, you don't see what's happening to the stable direction. Okay, now actually interesting examples. What about partially hyperbolic maps? So by partially hyperbolic, I mean that there is some hyperbolic direction, but there is also some neutral direction. So one case of neutral dynamics would be the rotation. One case of hyperbolic dynamics would be the expanding map. So you could consider, for example, mix of those two. For example, circle extensions. So one example of this is circle extensions. So it works like that. You take any map that you like. We are going to take the unique map. Let's say T. And then you are going to add a sort of rotation to it. So for that, you fix some map to. Let's take it whatever, smooth. Okay. And then the circle extension is going to give a scoop product of the moving map and of the rotation by 2 of x. The associated circle extension is, let's call it F. It goes from the 2 torus to itself. It takes x and theta plus it to f of r, and then theta plus 2 of x. So you see, in the theta direction, the dynamic is neutral, but in the x direction, you are expanding. So it's not clear what's going to happen. Is the neutral direction going to win, or is the hyperbolic direction going to win? It's not clear. Another very famous example of partially hyperbolic dynamics is what we call hyperbolic flows, which have actually bad names because any flow in the direction of the flow is neutral. So this is a bit misleading. But they are actually themselves partially hyperbolic, which is why it's difficult to study exponential mixing for hyperbolic flows. But it's easier for me to explain to you this case because the computations are a little bit easier. Okay, so intuitively, what do we expect? Let's do some drawings again. Let's try to find some intuition with our eyes. So depending on the choice of tau, we are not going to see the same things. If tau is constant, then what's going to happen? Let's take some set A. So it's a diffeomorphism. No, it's not. But whatever. Let's take the forward orbit. Okay. Let's take the forward orbit, and it will give us an intuition anyway. So you start from a cube. When you iterate your dynamics once to the future, say this. Okay, so this is the x direction, and this is the theta direction. In x, you are going to double your size. And in theta, you are just going to translate, but since tau is constant, just translate. So you are going to be transformed into something like this. And when you iterate again and again and again, you see that this is not going to change in side, but this is going to double each side. So after a little while, kind of A will just look like this. And then when you iterate, you will just translate up, down, this whole thing. So you see with your eyes that you are not going to exponentially mix because you're not feeling everything. So we expect at least that it's not mixing. Now, if you take some generic flow, again, this is its direction, this is theta direction. You start from a little q, and you go forward once. Then again, in this direction, you will double, so nothing changed, but the taux that you add will change when you go here, but actually you will get something like this. You have a little wiggle, which is given by 2. And then when you iterate it again, you can expect this little wiggle to be to become higher and higher and higher, etc. So after a while, if you continue to iterate, maybe you will see something like this, and then you will come back the other side, and maybe like that. And then after a little while, you will feel everything eventually. If two is, let's say, generic, or maybe random, you maybe expect this. But you see that it's not going to be very easy this time. You can again see it with the rest. So, but I think this encapsulated quite well the intuition of the kind of proof that you want to do in this kind of settings. When you have those partially hyperbolic dynamics, what will allow you to prove exponential mixing is a sort of kick in the neutral direction given by the other directions. It's it's something in X that gives you some twist in theta. There is some sort of twist like that. Just so you know, it's not going to be useful for us. In the case of hyperbolic flows, this twist is calculated using the notion of temporal distance function, which is why everyone is studying the temporal distance function when we are doing Dolgopyat estimate, exponential mixing, etc. Okay, let's do some computations. We have alpha. So, how to prove something? The answer is what we call Dolgopyat estimate. So, in this specific case that I am looking at, I forgot to tell you, of course, there is a measure which is invariant by f, which is the level measure of the torus. So I mean exponential mixing with respect to this. In this specific case, because I choose to be as elementary as possible, you could go, I think, quicker. Since you work with the level measure, there is probably a way to use for coefficients, stuff like that, to accelerate the proof. But I want to show you the general proof, which is more robust. So I'm going to do Dolgopyat estimating for question.
If this mixing is the big measures only according measures, society.
What do you mean?
If the system is mixing, or if the system is avoided, the big measures the measure such make the system is
I'm not sure I understand what you mean. Everything I'm saying can work for any equilibrium state. I mean, all of these works are way more general measures than them.
change another measure and still make the system to be equal. And it's other if the C is not is for some C is a measure can accept the base measure also make the system to be equal, or the big measures only measures to make the system to be equal.
So specifically,
Yeah.
no, I mean, so you can take any variable measure here, which is reasonable, and then you take d mu theta, And typically that's what you want. But indeed, in the neutral direction, I think you want to. Yes. I think here you will keep prevailing. Yes, I think it's important actually. It may be. Okay, so let's do some computations. So fix some maps. H1, H2 with whatever regularity. So let's say CP, for example. And now we consider and we want to say something. Okay, so the first thing that we should do is try to compute Fn of x theta. So it's not very difficult. I can maybe decompose it a little bit. Let's say here. So you have f of x theta, which is f of x theta plus tau of x. And if you iterate 2 times, you see that we get f2 of x, and here we will get theta plus tau of x plus tau of f of x. And if you iterate again, n times, and then the rest here, you will get fn of x theta plus a sum that I will call it a sum, and it is called a sum, which is just sum for k between 0 and n minus 1 of 2 of f of x. All of the computations that we here, you see very general and not even use the map, just to do a simple case. And again, you can replace this by any measure mu that you like, as soon as it is reasonable. Okay, so this is equal to this equal Peter King. Equal x equal theta. Okay. And now, because we use the Lebesgue measure in theta, this one is actually important. We can use Parseval to write this as a sum of Fourier coefficients. So let me define some notation. When psi is some number in Z, I'm going to denote by C, I don't know, C psi of H1 of X, whatever, something like this. This is the Fourier coefficient for X in theta. So X minus 2 pi by Xi theta theta. Up. So you pick X, you look at this function in theta, and you can decompose it using Fourier series, and this is the Fourier coefficients. So now you can use Parseval. This is decomposed using the Fourier coefficients. This is also decomposed using Fourier coefficients, so that you see that there is a phase that will come out in the exponential. Let's call all of that n like mixing. In the volume X, and then you have a sum. So our psi in Z. C psi of H1 at Fn of X sig psi of H2. Okay, maybe there is some gates. Okay, it's not very important. And then you have 2 I psi, maybe it's a plus, not very important either. And then Sn2 of x. Yes. So that's what you get by using personal. And now the zero. You can put the psi outside. And then you see that you have something that looks very much like the quantity that we use for exponential mixing just for the doubling map. But we just have a supplementary twist that we need to take care of. So I'm going to put the sum outside. The psi equals 0 term is a bit special, so I'm going to write it. Okay, x is this one. So C0 H1 and x C0 H2 x dx plus the other part sin z minus 0. And then you have, I will write it here. Sig psi H1 and x sig psi H2 x and then to twist minus 2 I pi psi Sn2 of x dx. Okay, this term is quite important because we can already control it. We know from what we proved just earlier that this is equal to integraling x of this times integraling x of this plus some exponentially small term. But integraling x of this is literally the integral of h1 on the two torus, because C0 is just an integral in the theta parameter. So this already converges to integral of h1, integral of h2, plus some exponentially small term, whatever. Okay. So the main problem now for us is to show that this whole sum go to 0 when n go to infinity. Okay. The point is that in some sense you don't really, because there is a sort of trick, you don't really need to care about what's going to happen in inside. I mean, you need to care. But since these are smooth, you can do some integration by parts, inside the Fourier coefficients. You can make some derivative in theta appear if you want. Let's say the second derivative in theta. And it will make some decaying term appear in front. So if you just reasonably bound this, even if there is some power of psi in front, you are still going to be happy, essentially. So you really only care to bound this as uniformly as you can in psi. Maybe there is some psi square in front of what you will get, it's not important. As soon as you have something that decays exponentially in n, you are going to be happy. So, okay, so that's good, but it does not seem that easy to do. So we reduced our problem to reduce to bounding quantities like that. I mean, you need to be AV. I cannot do everything, of course. So in the end, what you are interested about is bounding these kind of things. I'm going to change the notations with some h1 effects, depending on the side actually, but these are going to be uniformly regular, whatever it details. Okay. But in the end, those are the kind of things that you want to bound. So how do we do? We can try to mimic what we have done for psi equals 0. So what we can do is make the transfer operator appear. So this whole thing, again, we can make a transfer operator appear like that n times. Okay. Here there is an fn of x in front, so it can factorize. And you get integral over S1 of h1 of x times this weird quantity, h2 exponential minus 2 I pi psi times Sn of 2, which is almost like iterating the transfer operator, but again with a twist, which is why we call these things literally twisted transfer operators. So I'm going to call this quantity Ln index psi, and this is the twisted transfer operator. Now the whole point of Dolgopyat estimates, okay, sorry, so this is n psi of h. The whole point of Dolgopyat estimates is to bound these twisted transfer operators. When you are able to do it, you say that you are found a spectator or something like that. It's interesting because when you try to prove exponential mixing for hyperbolic flows, the path is not the same, but you can also reduce to establishing bounds for these operators. So they are natural in this sense that for different kind of dynamics, these guys may appear all over the place. Okay, so a formula for this is the following. In the case of the Budapest map, okay. So you have your twist to I pi psi Sn of 2 at Gax and h of Gx. And the point now is to bound this thing. So the goal, okay, let me first add one more line here. Now, if you want to bind this, you just need to prove that this goes to 0. So it suffices to prove it for the L2 norm. So you can just use Cauchy-Schwarz, and then bound by the L2 norm of x1 and the L2 norm of this thing. If you are able to show that this L2 norm decays in n norm exponentially fast. So as soon as you are able to prove something like this, for example, you can allow for some power because of the trick I told you earlier. As soon as you are able to do something like that, you need to have some control in the norm of h. I don't want to go into too much details.
But L is a fancy L.
Yes, I mean, I don't have that many L's in this story, so it's fine. Okay. Now I need to actually do the Dolgopyat estimate. So all of this is supposed to be very complicated, and once you are there, the whole proof is very long to establish the Dolgopyat estimates. But there is actually a couple of shortcuts that you can find that allow you to go way, way quicker. I'm going to use a shortcut by Jialun Li, which allows to reduce 30-page proof into a 10-page proof, essentially, something like that. I mean, well, you need some other black box. Yeah, I guess it's not too much. But in this case, it's going to be very fast. Okay, there is also something that you need to believe me. So, believe me, you can reduce to the case where n have order of magnitude log of xi. And if you find some decay in n or xi, it's enough actually. So I'm just going to say already the method to reduce to this case is to use pure from Frostman and last layer vehicle. But it's not that interesting in this case. I just want to talk about. Okay, so let's just open this to norm and see what happens. I try to do quick. Okay, so this is equal to some equal. Okay, this is my palette. Up. Now, the square, the modulus square is very useful because you can bilinearize it. Okay? So you get a double sum, and you can put the sum in A outside. So after expanding everything, you get something like this. Integral, exponential, 2 I by x side. And here you get a very important quantity, which can be interpreted as the temporal distance function when you are working with flows. There you are there. I think you see where decay going. GA is very, very much contracting, so it is almost a constant. Okay, so this is 1/4 the sum over AB over AN of H at GA 0, H of GB 0 plus some exponential factor times this interval, which is now the main attraction. Okay, so once we are there, this begs us to use some non-stationary phase, stationary phase, whatever. So you just need to study this phase here that I'm going to call phi phase. If the derivative of this do not vanish, you have decay like convex psi. If it does, you are just going to throw it away. And what you cross fingers is that for most words, you will be able to use this for decay now, and the other will be error terms. There will be not that much words. Doesn't allow you to do it. So this shortcut specifically was found by Jialun Li, and because in a way more general setting, if you work with some dynamical system F with a measure mu, and you happen to know that the measure mu have some Fourier decay, then you can prove these Dolgopyat estimates using exactly the same argument, Helsinki plus mu. And let me also say that it works also if the measure mu is linear, because if you have bound for the derivative, maybe you can try to do the same thing for the second derivative or something like that. So actually, this argument can be used very, very generally, I believe. But you need to use Fourier decay. So there is some work to be done at some point. But sometimes one of the two is easier to establish than the other, and then you can use one to prove the second, or use the second to prove the first. In this paper of Jialun Li that I am talking about, this is what he has done. So he proved Fourier decay, and then used it to establish the Dolgopyat estimates. now it's going to be pretty nice. You can now by like whatever, something like whatever size plus the probability that you cannot use it, which is the probability that this thing vanish at some point. Whatever. Let's say this. Okay, so you want something a little quantitative, so you can make like that. If your derivative is larger than 1 over square root of psi, then you get 1 over square root of psi as a decay bound, else you have these two bounds. Okay, I promised you something related to dual IFS. So where is it? It's there. So what is this thing? Let's only keep one of the two parts, okay? Let's only keep this thing and compute the derivative and see what happens. So if you look at SL2 composed with GA and you take the derivative, what is going to happen? So the Birkhoff sum is 2 of f x, f of x, etc. But here you have inverse branch, so you are going to make disappear some parts of the inverse branch. You get AK, A1, something like that. Okay. And you take the derivative, which is derivative of 2, j ak a1 x, derivative of j ak a1 x. And now maybe you are recognizing the dual IFS already, maybe not. This is a generalization of the quantities that appear in the dual IFS. So if you take 2 equal to log of the derivative of your dx, then this is exactly HA. So that's it. So that's what I wanted to explain to you mainly, is that these quantities were introduced as to be at least since Dolgopyat. So now the question is, how do you prove this? You can see that this now can be just interpreted as a Frostman bound on the dual attractor in some sense. So this is just a regularity bound. If you are able to prove in some sense that your dual attractor is alpha Frostman, in some sense, in this kind of sense, then this will be bounded by 1 over psi alpha over 2, and you are done. Another question is just how do we prove these kind of things? Well, just by some separation condition, for example, it works. So in this case, the separation condition that people used to use is called uniform non-integrability, because there is some geometric interpretation in the case of flow in terms of non-integrability of some formations, of some distributions. So, okay, very nice. So, the separation condition is for uniform non-integrability. And it says the following: there exists C0, there exists N, such that for all N larger than N, there exists A and B in your alphabet, such that for all X in your space, these quantities are C0 for all. So if you think about these quantities as elements in some attractor, you can think of a sort of a Cantor set, maybe with overlaps. You have here you have S12 composed with JA, S12 composed with JB, here you have S22 composed with JAA, etc. Unity tells you that at some depth, you have two branches that are C0 far away. And since you are working with some technical and IFS, whatever, this separation condition is going to be true at any scale, which is going to allow you to prove these regularity estimates, Frostman regularity stuff.
Basically, the same neural attractor as normal signal.
No,
Use it.
no, it might happen that all the functions in the dual IFS are intersecting. And this one says that one function is strictly above of the other one in the dual, in the other.
Yes, so let me just say that this can be replaced by there exists, and this is the same condition.
What?
These are equivalent.
Really? Okay.
Yes, yes. Okay.
So maybe it's sorry. So basically what you're saying that if the dual IFS attractor is not a single, then there are functions strictly below and above each other.
Yes, yes.
So, yes.
Yes, okay.
So I should say it's not the way I think about it most of the time, but yeah, I don't know, maybe yes.
I guess it just comes from the geometry of when you have something distinct, you can just push it forward to more levels, and you can build words with these in them, so that eventually everything has, at least large. At every level, you can find some.
Sounds good.
That sense to say that this is, you don't need all sufficiently large and it's many and.
Yes, you're right.
But they're all equivalent. So,
Yeah.
So this is like the strongest version, but in fact it's equivalent to the many and there exists an X.
Yeah.
It's the same as for all sufficiently large and are all X.
Okay, yeah, so.
Okay, no, but you're right. Technically, you want infinitely many ends.
They're all the same, that's the point.
Okay. We need to think about it. Okay. If n is large enough, then I'm convinced I think. But if you put this for equal way,
because of the
no,
IFS.
it's But okay. Good. Just to conclude, so you need allow you to put this down directly. This is something that I've done in my PhD under the name of trilemma. Because at the time there was no dual IFS, so I could not write it regularity for dual IFS. And what I wanted to say also is that, as you know, union is typically equivalent to your IFS, your base dynamic being conjugated to something which is affine or linear or something like this. So this is, I mean, okay, when specifically when you work with two equal this, I mean, or your dual IFS, okay, whatever, they know these figures. I think I need to, let me just check. Yes, let me just say, okay, that in general, you need still to be C2, and the best way would be to take two analytic. So when two is analytic, you have non-usual, which is equivalent to two being homologous to a locally constant function, which means that there exists a locally constant map kappa and some older map theta, such that you can write this. And when you apply this to specifically two equal log of the derivative, you recover that this is in fact saying something about the conjugated to some self-affine. Yes. Okay, and thank you very much.
Basically, this is again just saying that if not uni holds, then you have a single. Yeah, the single point time conjugate gives you the conjugate map to self-time mapping.
I believe you. I think that this is a coverage condition.
Yeah.
But
Yeah, but if you think about it this way, then if you are a singleton, then your neutral part in your dynamics can be conjugated to be actually a irrational rotation. And this is why it destroyed. But if you cannot conjugate that guy to a irrational rotation, then yeah, then this is why it happens. That's cool.
Yeah.
Kind of on the board you had over there, you kind of alluded to the fact that you have this space function which is given by what is phi AB, and if you can bound the derivative from below, you could follow this like van der Corput, which is what you need. But somehow you alluded to some way you can make it work for more general measures. So how would that go? So I have my e to the 2 phi I sine phi d mu, and I know my phi satisfies this non-constant notation.
So
What's the trick?
exactly in the same way. So if you have a measure mu, and so okay, the way I write my Fourier decay statements, typically I allow for the phase to grow a little bit in each side. So, and the point is that it's to allow you to do this kind of thing. So, typically, if you allow the derivative to be a little bit growing or a little bit decaying, you still get some uniform Fourier decay. And so that's essentially the trick there. Then if your derivative, instead of being this, you replace by that, epsilon, and finally you can use the result.
I guess I'm just. But I want to know how you prove that somehow. Yes.
It's complicated. It depends. So in the linear case, it's it's some product element and stuff. Yeah, so in this case, it's really a shortcut. In the general case, not really. It's interesting because it means that somehow those two problems are reformulation of the other, which allow you to think of it in a different way. Yes.
I have a question in the simplest setting of W map. If you want to prove the exponential mixing for the equilibrium state, which probability of equilibrium state will play the role for this? You can approximate your Riemann integral by Riemann sign an exponential error.
You just need the Perron-Frobenius square, I think, and that's all. So I'm just going to write it down. So in general, when you have mu an equilibrium state, you can look at the precomposition operator in L2 of mu. And by definition, the adjoint is what we call the associated transfer operator. So this is the definition. And Perron-Frobenius square is a theorem that tells you literally that this quantity converge to the integral of the H integral. So
what are the three?
And okay, it depends on the regularity of H2, because the proof is very, very close to what I explained to you earlier. If H2 is only continuous, you just get some speed like that. But if H2 is older, then you get this kind of
So this doesn't, the PFR or PFR doesn't hold for every equilibrium. You need the potential to be older, right?
Yeah, I only work with older potential, so I hope that's a very good state. It's very, very general.
Yeah, already.
Essentially,
Yeah, thank you.
So this proof was trying to show exponential mixing for these, what we call them, the partially hyperbolic systems, right, under some assumption on tau. And then, so the idea is that if tau satisfies certain conditions, then this unique. Oh, okay. So do you have some specific conditions on tau which will guarantee uni and therefore guarantee?
Yes. So typically, that's why I like to think about it this way. If you write it as a cohomology condition,
Oh, I see.
yeah, you can check it by looking, for example, at periodic points. compute some multipliers and stuff like that. Because okay, in general it may be a bit complicated, but in this very specific case, this locally constant map is going to be, I think it's actually going to be constant in the case of the 2D map. So you just need to find two periodic orbits, compute the Birkhoff sum at these periodic points, and if it does not give you the same value, then you're done. So you can check it in this kind of way. If you work with more complicated dynamics, it may not be that.
But the periodic points, that coding has to be a permutation of one of the other, they can't just be arbitrary periodic points.
Yes, you can do it that way, but if you are close to a literally constant map, then you can take anything you want. And also, if you already know a marker partition, you may know how many locally constant parts you will get. And if you have n locally constant parts, you just need to find the n plus 1 values, something like that. But it can be not completely clear how to check this in general. But when what you are studying as a clear dynamical interpretation, for example, for Julia sets, these kind of things are always true as soon as they were not conjugated to z to the power t or something like that. So it depends on what you are looking at, I think. It's essentially a nonlinear condition. Yeah. But I guess what you could do, sorry, is if this is true, then you are conjugated to something self-affine or something like that, and then you can use linear versions to still get Fourier decay. So maybe you could combine the two and get a very general Fourier decay statement.
But sometimes this is a very good rare condition, so if we take a kind of tau with the unreasonable parameters, can't we? Then this kind of thing will not perform.
If you choose to as random, it will never happen.
Right, other questions? If not, let's thank Gaétan again.